Welcome back to the Lowdown on Physics. This is screencast number 8 in a series on motion for Unit 3 VCE Physics. Today we will be looking at Hooke's Law and elastic potential energy. In Unit 2 you would have looked at Hooke's Law, and this is the relationship between the force and the extension of a spring. Now what this law states is F equals negative kx, where F is the force, K is the spring constant, or sometimes called the force constant, and X is the amount of extension or compression. The spring constant K basically tells you how stiff a spring material is. It also has the units of newtons per metre. For materials that will obey Hooke's law, we get a linear graph, that is, a linear increase in extension per given unit of force. Double your force, you get twice the amount of extension. Note that if you exceed this past the elastic limit, then what will happen is you will permanently stretch the material. It will become permanently distorted, and after that it will no longer obey Hooke's law. When we stretch or compress a material, we basically give that a stored energy. We call that elastic potential energy, and like gravitational potential energy, it's something that we store temporarily, and then when we release that energy, when we send it back to its normal position, energy is released, work is done. Okay, you've got to keep that in the back of your mind, that any time that there's a change in energy, there's going to be some work done. So how do we calculate work done for a spring? So calculating work done in a spring. Now we can't use work equals force times distance, and that's because we don't apply a constant force. The amount of force varies, or as the force varies, the distance varies. So how can we calculate it? If we come back to the work force graph, then the area under that is a triangle, so we can actually use work equals a half times force times the distance. But if we remember that force equals K times X, we can substitute Kx in place of F. And that gives us the equation work equals a half Kx squared. So as long as we know X and the spring constant, we can calculate the work done. Alternatively, if we know force and the amount of compression or extension, we can calculate the work done. So let's look at a pretty basic example. Using the work below, determine the amount of work done when it's extended by 20 centimetres. Units, always check your units. So we want a half times 0.2, so that will be 0.1 times 30, so we have 3 joules of work done. Okay, quick case study of a pole vaulter. Let's have a look at the amount of energy that's stored for a pole vaulter. So a series of energy transformations occur. So before the jump, we have kinetic energy of 1470 joules. We've got gravitational potential energy of 710 joules, no spring potential energy. The reason there is gravitational potential energy is because the centre of balance of the person that's about to complete the pole vault could still fall over onto the ground. So from about their waist, somewhere around that height, they have gravitational potential energy. So we have a total energy of 2180 joules. After, as they put the pole down, a lot of the kinetic energy gets converted to spring potential energy, and then that gets converted at the very peak to be a very small amount of kinetic energy, barely moving horizontally, mostly gravitational potential energy, and all the spring potential energy is then being converted back to gravitational potential energy. Here we notice that there is 2,970 joules of energy, total amount of energy. How is it that we have more energy after than before? And the simple explanation is that not all of the kinetic energy is responsible for getting that person up and over the bar. They use a lot of their chemical stored energy and convert that into kinetic energy, pushing with their arms, etc., to get them up and higher. So we do actually have more energy there because of energy that we're not accounting for in this first case. That's it. So this will be where we do the majority of our questions. It will all be about converting spring potential energy to kinetic energy into gravitational potential energy, and all the conversions backwards and forwards with work. That's where the money's going to be in your exams, so get used to being able to switch between the different forms of energy. See you in class.